All right, we're going to go ahead and get started. Thanks everybody for joining. I know we'll have other people trickle in. We had about 30 RSVPs for today. This is our second session of the Epiphyte build, where we check in every couple weeks to give a status report on where we are in the build process. This is our first build of the prototype of our open source DAC system Epiphyte, being built inaugurally in Philadelphia at the University of Pennsylvania Department of Chemical and Biomolecular Engineering. So we want to give them a big shout out and thanks for hosting us. And so what we do during these calls is we kind of, again, give a status update, but we want to involve folks who show up because as we go, we have questions, we have pivots that we're going to make, and we want to be able to get some input from our audience. And there's multiple different ways of doing that, both today, but also on our forum, which when we get to that, I'll drop some links. And so excited to be joined by David and JP and Ling and Chuck, who have been moving this project forward. JP and David and Chuck are in Philadelphia, actually have been going to the lab the last couple of weeks and putting this baby together. And so we'll be reporting on that today. And that's what we'll be up to. Let me just advance my slide here. We're going to go over, oops, sorry, a little slow screen here. We're going to go over the just the status on the basic mechanical assembly, which we've made some really good progress and are on schedule for. And JP and Chuck will lead us through that. And then the latest development is David has been working on the heating system, just the initial prototype for that. And he's going to show us his progress, his results, as well as some questions that may have come up in the process, which hopefully you guys can add some thoughts and insights to. And then we're going to open it up with just a discussion and kind of talk through, and then talk a little bit about next steps and maybe identify particular current needs that we actually have that maybe our small but growing crowd can help out with. Now, one of the things we plan to do with these check-ins, which we intend to do bi-weekly, probably on Thursdays, we'll stick to this time. It was Wednesday last time, but this is a better time probably, is have special guests, people with an interest in the subject and relevant expertise who can kind of be the first responders after we hear from the team here about where they are, who might be able to give some insights, ideas, or ask further questions. And as our first guest, appropriately so, I think it's just Mike. Fiona's not joining, but we are absolutely thrilled to have Mike Bwondera from Octavia Carbon, Sub-Saharan Africa's first direct air capture company, and now one of the fastest moving DAC companies in the world with close to 30 employees. And I was fortunate to meet up with Mike and the Octavia team last week in Nairobi during Africa Climate Week, and was able to see their factory with my own two eyes. They're dear friends who are very much part of the OpenAir family, and their early prototype that they built called Thursday was actually a big part of the inspiration for Epiphyte. So really excited to have Mike, who is the one of the co-founders, the first three people in the building. And he is does many things there, but he's the director of R&D. So he's going to be giving us some feedback on what he hears today. Mike, how you doing?
Hi, Chris. Hi, everyone. Doing well. I hope you're also doing quite well. Yeah, nice having you here over the past week. It was really enjoyable. And yeah, I'm looking forward to the session.
Yeah, thanks so much, buddy. And so what I was going to do is just give people a little bit of a couple looks. Again, as I said, you'll see the family resemblance between Epiphyte and Thursday today, but just a couple of pictures from Nairobi. This was a huge moment for me. I usually just see these as images, and I was able to pop by, again, their factory right outside of Nairobi. That's Duncan, who with Mike is the other co-founding engineer with Martin Freebiller, who's the CEO. as I was able to touch Thursday myself after looking at it for about a year. And one of the things that just absolutely kind of blew my mind about Octavia in general, but seeing the fruits of their labors, is how quickly they have moved. They now have a giant manufacturing facility where they have progressed from Thursday. And you can see on the left there was another earlier prototype that was the sort of the graduation from Thursday. And what you see me standing there in front of is the actual commercial product that they're still tweaking, but this is what's going to be deployed in the Great Rift Valley, hopefully in 2024 as a pilot. So it was just absolutely amazing to meet with the team and to see what they've been able to do. And so definitely check out octaviacarbon.com, and I'll drop the link in a little bit to see their progress. But keep your eyes on them. It's one of the most exciting DAC companies in the world with an amazing group of people. Mike, did you have anything you wanted to add at all just about Octavia, or anything you wanted to say?
Thanks, Chris. You've actually done quite a good introduction. So Octavia Carbon, we're a team of around close to 40 people right now, actually. We actually just had some new members join in this week. So we started operations in June last year. Start of June last year. It was the three of us, as Chris has said, Martin, Duncan, and I. And we've grown quite exponentially to where we are right now. Most of the team is comprised of engineers and technical staff. We have around 22 technical staff. The rest of the team is mainly on business development and such. And so we are planning to deploy our first pilot that should be able to capture 1,000 tons of CO2 in a year. And we want to deploy it in the Kenyan Rift Valley, mainly because of access to geothermal heat, which is waste heat in our case, and also the geology, the access to the geology in the Rift Valley here in Kenya, which is actually a really good carbon sink in terms of the having basaltic rock formations that can actually act as reservoirs for permanent storage of CO2. So I think that's it. We'll definitely get to interact more during the session, and looking forward to it.
Excellent. So awesome to have you here, man. So hang tight. We'll have you really eager to get your feedback on how far we've come so far. One of the things that's come up, Mike, you and Duncan were just telling me about Nairobi, about the fail points around vacuums and stuff like that. And that might actually be something that comes up today. So eager to get your thoughts on it. And folks, as we go, again, we're going to have a discussion here. Feel free to pop thoughts or ideas into the chat if you want to, or into the Q&A, and we'll address those shortly. All right. So team, if you guys want to turn your cameras on, because we'll go ahead and get right into it and turn our attention back to Epiphyte. Some of you may have tuned in a few weeks ago when we did our kickoff webinar, where it's been recorded and it's on the Carbon Crowd website, as well as the OpenAir YouTube channel, which kind of covered the objectives, the origins, and a bit of an overview of the design that we're starting with. And again, with this first build, what we're doing is we just want to take what we have on paper and build a unit, so to test and make sure it works and tweak it, and then create the full documentation that will allow others to build it. And our next build locations, keeping that secret right now, but we have at least one confirmed, will be a replication of what this team did. And then as we do subsequent future builds, every 2 months, we just keep going and going and going. We pick a different optimization theme. So might focus on things about how to make it more energy efficient, how to build in storage, maybe how to make it renewable energy powered, how to do MRV. We'll determine those as we go, but it'll continuously evolve through a group effort, building new systems every 2 months in different parts of the world. So what we're going to do is we'll start off first. It's been an active couple of weeks at UPenn. You see pictures of Chuck and JP there, who've already been in assembly mode. And so I wonder if JP and Chuck, if you guys want to just share some kind of high level thoughts about how far we've come in the last couple of weeks.
Sure. Thanks, everyone. I'll start with just a little bit of the sorbent panel, and then Chuck can probably jump in on the broader system components. So, the big component I think for assembly has just been dimensional fit. So the tolerances between how big or how small the sorbent panel can be are pretty tight. So I actually found that we designed the different components to be just about 1/8 of an inch too big. So I've been sawing down the different components on at least one side just to get a better fit. Even though we were able to kind of force the frame into that panel opening space, it was starting to bulge the unit, and so you're starting to get more openings that would have to be sealed up. So shorten that down, so it's actually a pretty snug fit right now. And I'm hoping that this week into next week is kind of the big leap forward. So hope to be able to kind of pour sorbent into the panel space and work with David so that we can run both thermocouples as well as the heating elements around the system, so that even if it's not a full component inside the actual unit, that we'll be able to start running heating tests and making sure the thermocouples work and that they're in the right spot. So kind of that big step forward, and then it will be documenting kind of the order of operations for how to assemble all the different components.
Let me just move back to this real quick here, just to give people a reminder or a higher level view of how this will work. So there's basically air flowing through both ends of the unit. And then that picture that I just showed, that thin little piece, is what you slid in there in the middle, which you said was a little too snug. And that has the sorbent embedded in it, right? So there's airflow passing through the sorbent, and that's how the magic happens. Is that a good way to summarize it?
Yeah, I think so. Yep, you'll have the air flowing through. As it is blocked by that sorbent panel, it'll pass through the sorbent and start to pick up CO2 from that. And then it will capture that as it's flowing through, and then we'll seal up the system and heat up the sorbent to release the CO2, and then pull that into a storage tank.
All right, excellent. Chuck, anything to add from your experience?
Sure, yeah, and unfortunately, I don't have a whole lot to present. I do have some photographs from the job site, from the lab, which I can share here momentarily. And I wanted to apologize on behalf of the team that we've been hamstrung by just various things like scheduling conflicts and not having the right tools on hand at the lab. That's kind of an oversight on my part. So I get there, I'm ready to work, and then I don't have something simple. So we're hoping to make some faster progress in the coming week. But what I did do was I was able to assemble the components that we had purchased, the main mechanical components, so that we have basically what looks like the little brother of the Thursday device, or the original Thursday device. And if you want, I can show you some of those pictures now,
Yeah,
Chris.
sure. Yeah, let's do that. I'm going to stop sharing mine. So you should be able to go ahead and pop yours up there.
So you should see some little thumbnails here.
Yep.
So this is the main fan. I built this little stand to put it on. You can see it looks pretty basic. It's just plywood and 2x4s. And so I mounted that on there and then attached it to the sorbent chamber with just some standard, duct sheet metal screws and some duct tape, because I was very anxious to turn the thing on and just have air flowing through it to see just, if it was going to vibrate or, just structurally what was going on. And I wanted to hear air flowing through the sorbent panel. This is a side view. And so I did take a video of that, which isn't really helpful. It's just fan noise. This is the sorbent panel pushed all the way in there. The sorbent panel doesn't currently have sorbent in it. And you'll also notice from these pictures that I don't have inlet or the outlet dampers attached yet. Again, that was a tooling issue where I didn't have what I needed to attach them together. But we weren't really ready to test the unit anyway. At that point, I think David pretty much has the controls all put together where he can, modulate the dampers and control the actuators and everything. We just haven't actually gone through the process of turning it on and putting it through its motions. And so you can see the sorbent panel is what, 2 feet by 2 feet, but there's this inner section that has holes cut in it. This is where the actual sorbent beads are going to go. And so we're going to have the ability to expand that later. If we decide to put more sorbent in it, we'll cut more holes in that. And so mechanically, that's kind of where we're at on this. I think JP is very close to the point where we can put the sorbent beads in it. And then what I'll want to do is do a static pressure test to see, just how much airflow we lose as we're trying to drive the air across the sorbent bed. And I think some of these issues, like, JP mentioned, we need to shave 1/8 of an inch off to make the sorbent panel fit in there. Those are all minor things we'll take care of pretty quickly and easily. I'm more anxious to see the heating elements go in place and watch the dampers actuate, and then start testing for vacuum pressure, which I know you were talking to Octavia about, and I've seen just from looking at the pictures of their subsequent versions of the Thursday device that it looks like holding a better vacuum is probably a top priority for them. And currently with our little brother device here, our little version, I'm not anticipating being able to hold a perfect vacuum, but maybe that'll be for the next team as we hand it off.
Can you, Chuck, real quickly say, why is it important to hold a perfect vacuum or a good enough vacuum? How does that functionally play into the overall performance of the system?
Sure. That question's for me. Is that correct?
Yeah, you guys know the answers. Anybody else probably, but go for it.
If the goal is for us to create a device where we're using a temperature vacuum swing sorbent, then we will be able to optimize the amount of carbon dioxide that we can pull out of the sorbent bed if we can put it under a pretty good vacuum. However, from what I understand from talking to a chemical engineer, he was explaining that we don't need an absolute vacuum to at least be able to drive some of that carbon dioxide out. And as we pull off the carbon dioxide that's coming out of it, there may be, if we don't have a perfect vacuum, then what we end up storing in our little storage tank, it just won't be pure CO2. It might be 90% or 50% or whatever that ends up being. And I think for the purposes of our experiment, we'll be happy to show that we've removed carbon dioxide from the air, even if our final product isn't pure CO2. And from what I understand from the chemistry, the deeper the vacuum we can get, the more pure the CO2 will be.
Yeah, and Mike can comment on that in just a minute. We'll take a little break between this section and before we go into David's test, we'll get some feedback from Mike on that because again, he was, not that I understood it, but he was talking about that when I was in Nairobi with him. Now, you had mentioned, Chuck, too, the sound part, the decibel level, and you thought it was quite loud sitting next to it. So I didn't know if you wanted to characterize that any further. How loud is it, or do you even have a video of it?
Oh,
sense of that.
So I appreciate you asking. I would like to qualify those statements. So I was, our lab is located near a mechanical room with a sort of a standard commercial air conditioning unit there. And so there's a constant drone of airflow going, through this air handler next to us. And the ambient noise in that room is significantly louder than this unit when we turn it on at, I'll call at speeds 1, 2, and 3. Until you get up to, speed 4, 5, 6, you can't even hear it over the drone of the air conditioning equipment. When you turn it all the way up to where it's putting out like, I don't know, 2000 CFM or whatever the fan is rated at maximum, it really is, you can really hear it. It's not like a jet engine or anything, but I don't think our device is ever going to be run at that level anyway. I think if we run it at maximum 400 CFM, we're probably going to get the results that we're looking for. Now, that said, if we do want to run it at maximum flow, and if it is noisy, I have a number of different sound attenuation options we can do to quiet the whole thing down, and won't make the unit a whole lot bigger. And it usually revolves around having an inlet duct and an outlet duct that are, a couple feet long and are a little bit larger than the inlet ducts that we have now, which are 10 inches in diameter. So we might be able to just put a basic sound attenuator on each end of it, and that could quiet it down by as much as half.
Wow. So I got to ask this too, and this is, very much the spirit of OpenAir, is about how people from different domains come in and apply their specific knowledge to make this increasingly more awesome. And you're an HVAC guy, an engineer, and has been in the HVAC world for many years. Those sound attenuation strategies that you just mentioned, is that something you pretty much pull from your practice in HVAC, or is it something that you've kind of thought up on the fly?
Yes, absolutely. And as a matter of fact, I've worked on projects similar to this lab where we're at, where a university lab where they're co-located with mechanical equipment, and the professor might complain about it. And so then we would go in and add sound attenuation and quiet it down to where it's, maybe at a ambient dB of maybe around 30, which makes it pretty reasonable for teaching a class.
Yeah.
And especially if the unit isn't right in the room, if there's just connected ductwork and you're just hearing the air noise as it's going through the ductwork, that's actually pretty easy to attenuate. As a matter of fact, this device, actually, I can stop sharing my screen now, but this device here.
Yeah, I think I put mine, but if you want to share another image, I can stop sharing.
Oh, no, I'm sorry. I didn't even realize you had taken back over. If we put this entire device into a square piece of duct that is 24 inches by 24 inches, to where the fan is now inside this square duct, and just line the inside of that duct with sound attenuation material, the whole thing would just get, factors quieter, and so the thing is, the fact that this unit we have now is the fan is only 10 inches in diameter. If you were going to put this in a building somewhere, it still takes up, pretty good sized space. And so taking that space up with a big square box really wouldn't hurt anything. And then the whole thing would be much quieter.
Yeah. All right. Good intel. So I just wanted to show this picture that JP shared with me shortly before we started, which I think kind of visualizes maybe some of the potential fail points for a vacuum, or some of the connections here are really, really important, I think, right? And I was just talking to Duncan about this in Nairobi last week. So JP or Chuck, I didn't know if you wanted to tell us a little bit about what we're looking at and how this is relevant to performance, some of these joints or connections.
Yeah, some of them aren't as easy. If you go to like the top right portion, you can just see up kind of at the top, there's a little piece, or sorry, top left. There's a little piece of light there. So it's just where the two sides of the housing are coming together. Just a potential area for gasketing. Similarly on the top right there, just where those interfaces are happening, whether either taping over those or applying some gasket material. But that's just area that once you start pulling a vacuum in, depending on how much vacuum you're pulling, you're going to start pulling more and more air into the system. Perhaps if we built a sorbent panel where we filled that entire middle space with sorbent and we were taking up, the all 4 inches of depth there, then that wouldn't be a problem because you'd just be releasing all the CO2 and there would be less room for air. But in something as small as ours, just something to consider.
Yeah, Eric had a point in the chat here that's pertinent. I think is he said, I suspect the vacuum pressure will influence CO2 absorption and stripping efficiency. So we ought to have a pressure sensor in front and behind the sorbent panel. Is that something we're already looking at as a pressure sensor? I know we're talking about CO2 and other temperature sensors, but I don't know if we've considered a pressure sensor.
Oh yeah, we'll have pressure sensors, CO2 sensors, temperature sensors on both sides of the panel.
Okay, great question, Eric. Thanks. Okay, well, maybe we could pause here for a second. I do want to ask about we'll after about the next week. We're looking at sorbent, putting the sorbent beads in there, and I'm curious about what has to happen with that in terms of treatment and all that stuff. But I'm wondering, Mike, this is all very familiar, probably deja vu to you, where you guys were about 18 months ago. But I didn't know if you had some initial impressions, and also if David, Chuck, JP, and Ling, if you guys had questions of somebody who was on this exact same course less than 2 years ago. So, Mike, I don't know, any initial thoughts on what you're seeing here?
Yeah. Hi once again. So yeah, I'm actually really impressed. Aesthetically, it actually really looks nice, better than the original Thursday. A few things I've noticed is what Chuck was talking about earlier on regarding the vacuums. You just need quite a light vacuum. Research shows about 100 to 400 millibars of absolute pressure is necessary, and it's kind of like an optimal range for a temperature vacuum swing system. And yeah, but we noticed that even getting to that point, any sort of minor leakage will actually be quite substantial. So one thing, so you tend to essentially, if you have a lot of leakage spots, depending on how easy it is to fix it, you might find yourself having to use some sort of filler like silicone or epoxy to just fill in those hard to weld gaps, or the gaps that you can't really put any sort of sealing or such. Another important thing to note is to be able to kind of get a net reduction in pressure inside the chamber. You'd also need to size a vacuum pump that can pull out quite large volumes, especially if you do tend to have a lot of leakage points. You actually need to have a vacuum pump that can suck out air much faster as compared to the rate of air influx. And I think one other thing I'd talk about is you need to be really aware of how to seal the dampers, the butterfly valves on each side of the sorbent chamber, right? O-rings are actually really important to have, especially for vacuum sealings. I think Chuck, you had shown some pictures of them, the dampers. Damper 1 and damper 2 exactly. So the valve themselves will have to kind of be lined on their circumference with some O-ring material to actually provide the proper vacuum sealing that you need. But yeah, one last thing I think I noticed that I actually just have to also touch on is Chuck mentioned quite correctly that you won't necessarily be running the fans at their maximum capacity. So one important parameter that you can think through, and especially using instrumentation, is the velocity of air that's actually flowing through your sorbent chambers. So literature and also through the tests we've done shows that you need just at most 0.5 meters per second of air velocity. And so what you can do is actually kind of look at that, multiply that with the area of your ducting to get an appropriate flow rate of air that you need from the fan. And then you can just regulate from that. I think you're using the Air Infinity fans that we had also worked with, and they quite have a good range of speeds and flow rates you can work with. So yeah, I think those are some of the things I noted.
Great. Any questions,
Mike,
guys?
Mike, what was that face velocity again that you recommended?
Oh, around maximum, it shouldn't pass 0.5 meters per second. Yeah, sorry, I'll be working a lot with metric here, guys. I can't do the conversions just right as currently, I mean, but yeah, just about 0.5 meters per second.
Awesome. Do you now that we have Mike, the Sorbent is the special sauce here, and we're just about to. I was fascinated when I was in Nairobi looking at, they have a dedicated Sorbent lab with all kinds of equipment and testing and heating and stuff like that, which I can share pictures of maybe later. But we're about to go into that. We're about to apply the Sorbent beads and test it out. Do you guys have any questions that you might want to ask Mike, or maybe Mike has some wisdom to impart on that?
I'm thinking.
You just put the beads in there out of the box, or do you have to do something to them? Or and Mike, you might even have some rules of thumb just around sorbent handling that might be useful. Lessons learned.
Yeah, cool. In terms of the beads, having sorbent beads, you could structure a sorbent bed in different ways. You could have finer powders, you could have larger granules or beads or such. And so you'd really want to be able to quantify the pressure drop. And I think you're probably thinking through that. We usually have this tool that we use, like some sort of equation known by most HVAC people in terms of quantifying the pressure drop across a sorbent chamber. Because essentially what happens is, as you pack your sorbent beads in the chamber, blowing air through it would tend to create that resistance or that pressure drop. And being able to quantify it is really important, because actually that also ties towards your fan selection, right? Because most of the time you size fans with their flow rate and the pressure drop they can resist. Beads actually have quite a low pressure drop, so I don't think it should be too much of an issue for you guys. But yeah, I think in terms of just packing the sorbent material inside there, I think that's one thing that I could point out right now. And also the fact that they are kind of arranged in a vertical manner. The sorbent is arranged in a vertical manner. You should be really aware of ensuring that even as you're packing the sorbent, it doesn't really sulk. It doesn't really sulk and try to bulge at the bottom and leave a space at the top of the chamber that you're packing it in, because that will actually create a lot of inefficiencies in terms of airflow.
Mike, is it okay if we share some video for when we get to that point? We might WhatsApp it to you, and if you have any guidance on that, when we get to that point, we'd obviously appreciate your wisdom. Do you guys have any questions based on what Mike just shared, or needs for elaboration or thoughts?
Based off of the notes that we had from the Thursday build and building off of that, because we read that you did have issues with the sorbent compacting down and bulging out, and we're using like a polymer film. So I think what we did differently just to see how it would change was we're using a metal mesh screen rather than a polymer for additional structure. The problem with that, though, is that then we had to move from using a fine powder as a sorbent up to a larger bead size. So interested in just your perspectives on what you have looked at with Octavia and how you went about making the choice between like a fine powder and beads, how that affects your pressure drop, and your total like absorptive capacity and some of those things for how you made those design considerations.
Cool. Yeah. So to start by the point on fine powders or beads, essentially, what you're trying to optimize on is the mass transfer. So how much CO2 can actually be taken up from a stream of air at a time. So fine powders tend to have quite a larger surface area for CO2 capture, and so that translates to better mass transfer. And so in simple terms, you tend to have shorter absorption times as compared to if you're using beads or larger granules, where the mass transfer would be slower. And so what would happen, you tend to have to run absorption cycles quite for much longer to actually be able to saturate the solvent that you've packed inside there. But yeah, larger granules tend to have quite more voidage within the chamber you're packing in. And so what happens is you have much less of a pressure drop, and in simple terms, you need less of the fan energy to actually push air through the system. And you can also kind of you have some leeway to maybe have a thicker sorbent packing inside your chamber. So it's kind of like an optimization between the two. I don't know if you guys have it, but I can share some equations. It's called the Egon equation, where you can just be able to quantify the pressure drop that's flowing through a structure like a packed bed structure, which will actually be really instrumental in kind of ensuring you're sizing your fan correctly. But yeah, I think that that answers that question. And also on the point on having that metal mesh, yeah, that actually also helped in our case. And it's actually I actually think the way you've designed it is quite shrewd in terms of having this large structure and then the opening at the middle, because it provides a lot of stability and rigidity to ensure that what you're packing actually really holds and doesn't bulge, because yeah, like you said, it offers quite rigid structure. So yeah, I hope I've answered your questions.
Yeah, thank you.
Excellent. All right, now let's move into another subject that, Mike, I know you will recognize. So one of the things that you did, Mike, in Octavia, you guys made a pivot from electro resistance based energy, and you're going directly to thermal because you're preparing to integrate this with geothermal, which obviously allows for both heat and electricity. But we're sticking with the original method because we might take a pathway here where this is solar powered or can be plugged into a wall, so it's appropriate to keep it electric. But David, our electrical engineer and seasoned tinkerer and hacker, has been in parallel to what JP and Chuck are doing, working on the first sorbent heating system, and he's going to give us some updates on where things stand with that. So David, you want to run us through? And I'm going to, as soon as I on the screen share, I'm going to share the links to your forum post, or if one of you guys wants to share David's forum post in the chat, that would be great if people want to grab that, and if they have any further thoughts, they can add them there. But David, yeah, how we looking on the sorbent heating prototype?
Well, it's working. I could burn my finger on it. Okay, let's see. This picture here is really kind of a schematic view of what we're talking about. That square in the middle is that sorbent panel that you saw in JP and Chuck's pictures. The yellow part is filled with sorbent. And so we need to heat it up with hot wires. And since we are trying to operate in a vacuum, we can't use anything that relies on blowing heat or anything like that. So the wires have to actually be in contact with the sorbent material so they can warm it up through thermal conduction. Now, one thing that's different from Octavia's design is, as JP mentioned, we have a metal mesh holding in the sorbent. And so instead of using the bare wires, I had to, let's see, can you go to those spools, Chris?
Go back to the spools, yeah, right here.
Probably the least interesting picture we have, but so the left spool shows the nichrome resistance wire, and it has a resistance of 0.4 ohms per foot, which means the whole length of it will have about 2.4 ohms. But the point of the picture is we need to insulate the wires somehow from the metal mesh. So I also bought a length of braided fiberglass sheathing that can cover the wires and provide electrical insulation at least, and hopefully they'll allow most of the heat through. And that's the part that wasn't too clear in advance for how that would work. But we needed some material that could handle high temperatures, and the fiberglass seemed like a pretty good method to do it there. Okay, next picture.
All right. Let me
Next one.
like delay here. Sorry. There we go. Oh,
Okay, so
all right, 1 second, Dave. I have a delay on my laptop, which is making loud sounds, but here we are.
So before we're kind of building things in parallel here. So before the system is ready to actually run the wires into the sorbent chamber, I wanted to build a test version on my workbench here. So I took the same amount of wire that would go into the actual sorbent, and I zigzagged it between these eye bolts on a piece of plywood, and connected that to the electrical power. And also you can see in the middle there are a couple of things attached to the wires. Those are thermocouples for measuring the temperature, and one of them is in direct contact with the wire, where I've removed some of the sheathing so we can measure the actual temperature of the metal. And the second one is on the outside of the sheathing, so we can see what the difference in temperature is as a result of the insulation. Now, I'm a little nervous about doing anything with 110 volts of line voltage anywhere where it's exposed. So I decided to operate this whole system from 24 volts DC. And so I bought a couple of DC power supplies, which I wired up inside a box to the from the line voltage.
This right here, David?
That's the one on the right. Yeah,
Yep.
I've got two different supplies. 24 volts, they're 250 watt supplies. So I figured that was the most power we might need, one for each side of the sorbent. And that's all bolted together so nobody's going to touch anything dangerous. And the 24 volts comes out of that to supply the heating wire. So next.
All right, let's see how long this takes. There we go.
Now, if you do the math, 24 volts across 2.4 ohms will give us 240 watts of power coming from the resistive wire, and that is probably a lot more than we need. So I built a way of limiting the amount of power, and that is, we call it PWM, pulse width modulation, where the 24 volts is switched on and off about 1,000 times a second. And I built a circuit that's controlled by a processor to do that switching. So if you look at the oscilloscope display on the left, the top waveform is the actual output from the processor, and it goes from 0 to 3.3 volts at 1,000 times per second. And I can vary the width of those pulses depending on how hot we want the system to get. So narrow pulse, less power; wider pulse, more power. And then the bottom trace, it's actually at a different scale, but that shows what's actually being imposed on the heating wires at the same time, and that goes from 0 to 24 volts. So we have, say, 240 watts coming out, but only for a small fraction of the time. So the total power dissipated is proportionate to that pulse width, which is called the duty cycle. And this, for example, it's on 20% of the time, so that's a 20% duty cycle. And on the right is just my hand-built setup, and that's all going to be soldered together, so it'll be all robust and everything when we take it into the lab and install it in the machinery. So next picture, please. So I did some tests where I turned the system on with 4 different duty cycle values, 10 to 40%, and I measured the temperature with those thermocouples and logged it over time. And you can see how long it takes for the wires to heat up. And the traces are shown in pairs. And in each pair, the bottom trace is the temperature outside of the insulation, and the top one is the temperature of the bare wire. So you can see we get some temperature loss through the insulation, which is not ideal. And I think in a future version, I would recommend finding another type of insulating material or a different layout that maybe doesn't require insulation at all. For example, if all the elements of the sorbent panel were insulating materials such as plastic or something. But I understand we went for the metal for reasons of rigidity. And the other thing you can get from this is you can see how fast it heats up. And this is just with the duty cycle at a constant value, but it suggests ways that we can control the temperature more robustly as part of a feedback loop, where maybe we could start out giving it a lot of power at a high duty cycle, so it ramps up fast at first, and then we dial down the duty cycle when it gets close to the temperature that we would like. So the eventual design will have actually a temperature goal that we program in, and we'll measure as part of a feedback loop the temperature, and we control the power to the heating wires in order to reach the temperature as fast as we want to, but without overshooting it. And I think that's it to present here.
So, Mike, Dave, it sounds like you're definitely satisfied with the results at this point. It's moving in the right direction, you think? It's becoming hot, and so far a level of success on this, we think, right? No giant flag so far.
That's right. No flags. Right. Nothing caught on fire.
That's the first indicator of success. So that's good. I'm glad you didn't catch on fire. Mike, what do you think? Again, familiar territory for you. You guys struggled with the electric resistance sort of approach, and I'm curious what you think of David's mod here.
Yeah, David's design is actually a much it's a neater design as compared to what we started out with Thursday. Yeah, and one thing that we were facing that's really important to consider, definitely through quite a number of cycles of tests, are the new chrome wires did tend to warp around whenever you supplied current to them. And so what could happen is so they warp and they start moving around, and essentially you could have 2 different wires kind of touching against each other. Now, if your insulation is good enough, that shouldn't be too much of a problem. The problem will mainly happen if the heat distribution through a sorbent material won't be even. But in terms of a safety standpoint, you never want an adjacent wire to kind of eat through the sheathing, like the fiberglass, the next wire, because if the bare metal nichrome wires actually touch, that would actually cause sparking, which is dangerous. Another thing I noted is we also thought of power regulation. I think as we kind of tapped it directly from mains electricity. Here in Kenya, we usually use 240 volts. So we tapped it from the mains electricity and just kind of like used a power regulator, a high power regulator to just regulate it, and same principle of pulse width modulation that David has just explained. But going forward, we actually noticed, and because we still kind of used the same feedback loop of temperature control in some of our process equipment, that actually going ahead and just getting off the shelf temperature controllers, they're usually called PID controllers, was actually really better, because they have quite a good feedback loop, in terms of you can actually just have a set point of temperature, and you put your sensing device, should it be a thermocouple, where you actually want the temperature, where you want to measure the temperature, and through some sort of tuning, and it would involve a bit of coding and such, you could actually have your PID controller just work on actually regulating that power. That's something you could probably use for a later build, but it actually just makes temperature control quite much more easier, as opposed to trying and essentially designing all that by yourself.
Excellent.
That's a good suggestion. What we're doing, by the way, is when we document this, we're going to say, this is how we built it. And by the way, this is how we recommend the next people do it, based on what we've learned.
Yeah,
That's
definitely.
the whole point of this one. Yeah.
Yeah, but I have to say that that has been really that's quite a good design. We're actually having quite some trouble in getting data in our first iteration. So being able to get that data is just shows quite a robust design.
Excellent. Cade put a couple of good. Our buddy in Puerto Rico just did have one comment here on the insulation is transferring heat, so the temperature outside will depend on the surrounding conditions. If there is free airflow around the insulation, then the temperature will be lower. Maybe in the operating system, heat transfer will all be radiative. So I'm not going to pretend I know what that means, but I know you guys do. So food for thought. So that's great. Okay, so that's where we are. Great progress so far. Did you guys have any other kind of thoughts that have kind of emerged in your head that you want to sort of raise, or are there big questions that you also have as we go into these next 2 weeks that's going to be more focused on Sorbent? I imagine sort of the software piece of this will be on the horizon too, right, David? So any thoughts from the team?
So this is to Mike, and you probably get this question a lot. Anyone who I give my sort of elevator pitch to about what I've been doing on this, a lot of times they interrupt me and they say, but what are you going to do with the carbon dioxide? What's the whole point? And I have to say, well, that's for someone else to deal with. We're just trying to take it out of the atmosphere right now, but there is a market for it. So I'm curious what you guys are planning on doing, or what you're already doing with the carbon dioxide that you're capturing.
Good. Nice question. So essentially, our whole model is to capture the CO2 and store it underground permanently. So essentially, thinking about, so we kind of want to create a net removal of CO2 emissions from the atmosphere. So we have this situation, especially in the Kenya Rift Valley, because of all the volcanic activity that happens there. Is we have some suitable geology that can actually store CO2. So essentially, we have these basaltic rocks that are basic in nature, and CO2 being an acidic gas, you can actually pump this CO2 underground, actually mix it with water to form carbonic acid and pump it underground. And so what happens is the CO2 mineralizes within the rock formations over time. So you kind of now have CO2 stored permanently and not re-emitted back to the atmosphere. So I have to point out that us being a dark company, we work on the capture side, and we have a storage partner who actually work on now sequestering this CO2 underground. So that's on currently what we are working towards. But yeah, we've also been thinking a lot and having conversations with various researchers on kind of now looking at the CO2 and looking at it in terms of creating value. So essentially, I know there's a lot of work being done on creating things like synthetic aviation fuels, especially for long haul logistics that are quite hard to have like electric alternatives for case in point airplanes. So there's a lot of work in trying to kind of have air captured CO2 and have other inputs like green hydrogen and such to create hydrocarbons, which can essentially replace the well-known model of actually having to mine hydrocarbons from underground. Yeah, so those are the two main cases that we're actually thinking about, both in the short term and long term. But yeah, there are also other avenues. Some people store CO2 in cement to actually get that permanent storage and also improve cement qualities. Others would just use the CO2 as a normal industrial gas to in beverage industries, in like for welding and such. And so there's quite a wide array of how you could use the CO2.
Yeah, and we'll definitely have a build around that. There's some ideas that have been surfaced around, carbonates, doing mineralization integrated into it. We have another member at UT who built a small DAC unit where he integrated algae, where the CO2 was going into that, and he dried the algae. So that'll be a fun turn that we take of ultimately figuring out, can we bring the storage to the unit and have it operate on a similar scale and figure out what to do with it. So very exciting thing to explore in a future build. Great. So we're almost at time here. This was fantastic. Really appreciate people for joining. I'm going to edit this video and post it to our YouTube and spread it far and wide and keep building. But please do, folks. We put some links there. There's the Epiphyte Forum, which is part of the OpenAir Forum. Please do join that. That's a great place to have an ongoing conversation. I also put our OpenAir Join Forum, which will take you into our Discord, where we all hang out and have active conversations around this project. So that's a great place to come in if you haven't already. And we will check in again in a couple weeks. And by that point, maybe before we jump off, what do you guys expect us to be showing in 2 weeks when we have our next webinar?
I expect that we'll have a sorbent panel with sorbent in it that will be able to look at the pressure drop across it, as well as we'll be able to start testing the heating elements and the thermocouples. So being able to look at kind of real time, how is the sorbent panel actually heating up? How is the heat transfer flowing through? What's our power consumption going into that heating element looking like?
Fantastic. David, what about on your side? Oh, I think you're on mute.
I agree with what JP just said. That sounds about where I think we'll be.
All right. And what do we think? We're about a month out, maybe, barring disaster or something like that. When do we think we might have because we have a very special guest, so I won't say, who will be here for the last webinar we do. He's a titan in the direct air capture field who will present our final design to. But what do you guys think our timetable is, maybe for putting a bow on this?
Well, I would say that if we reach the goals that they just described in 2 weeks, and part of that would be hopefully I should meet my goal of having the dampers in place and to where we can actuate them open and closed, and everything will be attached mechanically. After that, I think it should come together fairly quickly where we can, be able to, if we have our measuring devices figured out, be able to measure that we've removed carbon from the air that's going through the machine.
Mm-hmm. I agree. And I'd like to point out that this isn't, I don't think of this as a once and done thing, that a month from now, if we have a working system, there's still a lot more benefit that we can get from it. There are a lot of tests that can be done to optimize the different parameters, the different methods of heating, the different levels of airflow. I'm hoping we could experiment with different sorbents. We haven't really been able to get our hands on anything other than the zeolite 13X, but if somebody is willing to provide us with some or donate it or tell us where we can get some, that would be very useful.
That will definitely be the focus of at least one build. And you're right, this is the very beginning, not the end. This is the kernel, the hello world, as we call it. So, but want to thank the team on their incredibly hard work here and the great progress we're making. I want to huge shout out to Mike for your imparting your wisdom, and hopefully you'll be following this project as we go, because we'll probably tap you on WhatsApp or on the Discord to maybe give us a little advice at different twists and turns. But fantastic progress, guys. Video will be up. Join the forum, and we'll see you in 2 Thursdays. Thanks, everybody.
Great. Thank you.